In this lecture we will discuss the memory hierarchy, and mainly cache memory organization. We will start with the explanation of the memory organization. Here you can see the different levels of memories used in the computers. Notice that from top to bottom the memory types become cheaper, with larger capacity, but also slower. We will climb up the pyramid starting with tape backup. In computers, tape backup is the ability to periodically copy the contents of all or designated amount of data from its usual storage device to a tape cartridge device, so that, in the event of a hard disk crash or comparable failure, the data will not be lost. The next step is the hard drive. A hard disk drive, also known as HDD, is a data storage device used for storing and retrieving digital information using rapidly rotating disks coated with magnetic material. The hard drive retains its data even when powered off. Data is read in a random access manner, meaning individual blocks of data can be stored or retrieved in any order rather than just sequentially. An HDD consists of one or more rigid rapidly rotating disks with magnetic heads arranged on a moving arm to read and write data to the surfaces. Today's hard drives can store thousands terabytes of information on a cheap price. Next, and today's most widespread memory, is the flash memory. Flash memory refers to a particular type of electronically erasable programmable read-only memory. It is a computer memory chip that maintains stored information without requiring a power source. It is often used in portable electronics, such as digital music devices, smartphones, and digital cameras, as well as in removable storage devices. This technology also is useful for computer basic input-output systems known as BIOS, modems, and video game cards. Today's flash can be as small as a coin and store TBs of information. Now let's see the upper part of the pyramid, where the memory is many times faster than the previous ones. Starting with the main memory, also known as RAM, refers to physical memory that is internal to the computer. The word main is used to distinguish it from external mass storage devices such as the disk drives. The computer can manipulate only data that is in main memory. Therefore, every program you execute and every file you access must be copied from a storage device into main memory. The amount of RAM on a computer is crucial because it determines how many programs can be executed at one time and how much data can be readily available to a program. Because computers often have too little main memory to hold all the data they need, computer engineers invented a technique called swapping, in which portions of data are copied into main memory as they are needed. It occurs when there is no room in memory for needed data. When one portion of data is copied into memory, an equal-sized portion is copied out to make room. Now, most PCs come with a minimum of 32 megabytes of main memory. You can usually increase the amount of memory by inserting extra memory in the form of chips. But more crucial for the efficiency of processes is the cache memory, used by the central processing unit of a computer to reduce the average time to access memory. It is a smaller, faster, and stores copies of the data from the most frequently used main memory locations. As long as most memory accesses are cached memory locations, the average latency of memory accesses will be closer to the cache latency than to the latency of the main memory. When the processor needs to read from or write to a location in main memory, it first checks whether a copy of that data is in the cache. If so, the processor immediately reads from or writes to the cache, which is much faster than reading from or writing to main memory. The probability that the required word is already in the cache depends upon the program and the organization of the cache. Typically 70 to 90% of references will find their words in the cache. We will show you how cache works in the next slide. On the very top of the pyramid is the processor register. In computer architecture, a processor register is a small amount of storage available as part of a CPU or other digital processor. Such registers are addressed by mechanisms other than main memory and can be accessed more quickly. Almost all computers, load-store architecture, or not, load data from a larger memory into registers, where it is used for arithmetic, manipulated, or tested by some machine instruction. But cache is without doubt the most important thing you can have in your processor. It really does improve the performance of your system. Let me show you how it does it. Now we have a good little diagram here. There is processor, cache, cache controller and RAM. The cache can do something called reading ahead. Let me describe you what does that mean. Here in RAM, files are broken into little blocks, generally into 64 kilobytes blocks of RAM. Let's imagine we have opened a file, and we start reading it. The first thing the CPU does is to search for the file in cache, but of course the cache doesn't have it. That is called a miss. So in the second process the CPU goes to RAM and finds it in there, but it can bring over only one block at a time. So it grabs hold of that block, transfers it back to the CPU, and it starts working on it. And this is where the intelligence kicks in, because the cache controller makes a very good assumption that if I used that particular piece of code related to that file, I might need the rest of the code related to the file at some point very shortly in the future. So the cache controller grabs hold of the rest of the file and moves it to the cache. When indeed the CPU needs to find the rest of the information, it searches first the cache, and it finds it in there. That saves it from having to go to RAM at all. The main question here is why the CPU just doesn't go to RAM, and there is a very simple reason for this, because cache is much faster than RAM. Now you remember that blocks of code is moved from RAM to cache, and that's where the replacement policy decides where in the cache a copy of a particular entry of main memory will go. But when the cache is full, a replacement algorithm must choose which items to discard to make room for the new ones. If the replacement policy is free to choose any entry in the cache to hold the copy, the cache is called fully associative. At the other extreme, if each entry in main memory can go in just one place in the cache is direct mapped. Let's begin with fully associative mapping. Its approach is to store both memory address and data together in the cache. A fully associative cache requires the cache to be composed of associative memory holding both the memory address and the data for each cache line. The incoming memory address is simultaneously compared with all stored. If a match is found, the corresponding data is read out. Single words from anywhere within the main memory could be held in the cache, if the associative part of the cache is capable of holding a full address. In all organizations, the data can be more than one word, that is, a block of consecutive locations, to take advantage of spatial locality. In the figure, a line constitutes 4 words, each word being 4 bytes. The least significant part of the address selects the particular byte, the next part selects the word, and the remaining bits form the address compared to the address in the cache. The whole line can be transferred to and from the cache in one transaction, if there are sufficient data paths between the main memory and the cache. With only one data word path, the words of the line have to be transferred in separate transactions. The fully associate mapping cache gives the greatest flexibility of holding combinations of blocks in the cache, and minimum conflict for a given size cache, but is also the most expensive. It requires a replacement algorithm to select a block to remove upon a miss, and the algorithm must be implemented in hardware to maintain a high speed of operation. As we said, there is another mapping method called direct mapping. The fully associative cache is expensive to implement. In direct mapping, the cache consists of normal high-speed random access memory, and each location in the cache holds the data at an address in the cache given by the lower significant bits of the main memory address. This enables the block to be selected directly from the lower significant bits of the memory address. The remaining higher significant bits of the address are stored in the cache with the data to complete the identification of the cache data. Consider the example shown in the figure. The address from the processor is divided into 2 fields, a tag and index. The tag consists of the higher significant bits of the address, which are stored with the data. The index is the lower significant bits of the address used to address the cache. When the memory is referenced, the index is first used to access a word in the cache. Then the tag stored in the accessed word is read and compared with the tag in the address. If the 2 tags are the same, indicating that the word is the one required, access is made to the address cache word. However, if the tags are not the same, indicating that the required word is not in the cache, reference is made to the main memory to find it. For a memory read operation, the word is then transferred into the cache, where it is accessed. Here is the direct map cache with a line consisting of more than one word. The main memory address is composed of a tag, an index, and a word within a line. All the words within a line in the cache have the same stored tag. The index part to the address is used to access the cache, and the stored tag is compared with required tag address. For a read operation, if the tags are the same, the word within the block is selected for transfer to the processor. If the tags are not the same, the block containing the required word is first transferred to the cache. There is a third type of mapping called set associative mapping. Its scheme combines the simplicity of direct mapping with the flexibility of fully associative mapping. It is more practical than fully associative mapping, because the associative portion is limited to just a few slots that make up a set. The organization is shown in the figure. The cache is divided into sets of blocks. Each block in each set has a stored tag which, together with the index, completes the identification of the block. First, the index of the address from the processor is used to access the set. Then, comparators are used to compare all tags of the selected set with the incoming tag. If a match is found, the corresponding location is accessed. Otherwise, as before, an access to the main memory is made. The tag address bits are always chosen to be the most significant bits of the full address, the block address bits are the next significant bits, and the word address bits form the least significant bits, as this spreads out consecutive main memory blocks throughout consecutive sets in the cache. Notice that the association between the stored tags and the incoming tag is done using comparators, and can be shared for each associative search, and all the information, tags, and data can be stored in ordinary random access memory. The number of comparators required in the set associative cache is given by the number of blocks in a set, not the number of blocks in all, as in a fully associative memory. The set can be selected quickly, and all the blocks of the set can be read out simultaneously. After a tag has been identified, the corresponding block can be selected. The replacement algorithm for set associative mapping considers the lines in one set, as the choice of set is predetermined by the index in the address. Hence, with two blocks in each set, for example, only one additional bit is necessary in each set to identify the block to replace. Now let's talk a bit about the problems that occur. When a data is written to the cache, it must at some point be written to the RAM as well. The timing of this write is controlled by what is known as the write policy. In a write-through cache policy, every write to the cache causes a write to the RAM. Alternatively, in a write-back cache, writes are not immediately mirrored to the store. Instead, the cache tracks which of its locations have been written over. These locations are marked dirty. The data in these locations is written back to the RAM when those data are evicted from the cache. For this reason, a miss in a write-back cache will often require two memory accesses to service, one to retrieve the needed data, and one to write replaced data from the cache to the store. The probability that the required word is already in the cache depends upon the program and organization of the cache. Typically 70 to 90% of references will find their words in the cache, called a hit, but the rest is when a reference to the main memory is necessary, called a miss. The hit ratio of a cache describes how often a searched for item is actually found in the cache. More efficient replacement policies keep track of more usage information in order to improve the hit rate for a given cache size. The latency of a cache describes how long after requesting a desired item, the cache can return that item when there is a hit. Faster replacement strategies typically keep track of less usage information. Or, in the case of direct map cache, no information at all, to reduce the amount of time required to update that information. The average memory reference time, as you can see, is a sum of the miss ratio multiplied with the time to make access to RAM, plus the time to reference the cache, if there is a hit, and last, some time for various secondary effects. If there is a hit in the cache, the first part becomes 0, and, as you can see, the memory reference time significantly drops. In other words, from top to bottom of the pyramid, every memory is a subset of the next in the hierarchy. The faster the memory is, the pricier it goes. But don't worry. Today's technology advances faster than it is expected, so prices are going down with each passing day.